For the past 20 years, physicists have been certain of one thing. The universe would expand forever, accelerating, and everything would end in absolute cold. But in 2024, new data shattered this unshakable belief. Could dark energy, that mysterious engine we call it, have stopped pushing the universe? If the latest measurements are correct, the universe's fuel is running out, and everything is hurtling toward a catastrophe much sooner than we thought. What happens if expansion stops? Will galaxies start colliding instead of moving apart? Will the end of time be not a freeze but a massive collapse? Today we're examining the biggest crisis in modern cosmology, the weakening of dark energy and the universe's inevitable Big Crunch scenario. If you're ready, let's go to where reality is tied down. First, let's understand the fundamental facts. The universe is expanding. This is one of the greatest discoveries of the 20th century. Edwin Hubble in 1929 observed that distant galaxies were moving away from us, and the farther they were, the faster they were receding. This is Hubble's law. Velocity equals Hubble constant times distance. So the universe is expanding in all directions. Galaxies are moving apart. Space itself is literally growing. But why? The answer: the Big Bang. 13.8 billion years ago, the universe was an infinitely dense and infinitely hot point. Then it exploded. It began expanding. And it's been expanding ever since. But here's the interesting part. The expansion should have been slowing down, because there's mass in the universe. Galaxies, stars, planets, dark matter. And mass creates gravity. Gravity pulls. It slows things down. So the Big Bang's driving force should weaken over time. Gravity should win. Expansion should slow down. But in 1998, something was discovered. Saul Perlmutter, Brian Schmidt, Adam Rees, 3 astrophysicists. They were studying supernovae, very distant supernovae. And they found something shocking. The universe isn't slowing down. It's accelerating. The expansion rate is increasing. This was absurd. Gravity should slow everything down. But instead, something was pushing the universe, accelerating it. And they gave that something a name: dark energy. What is dark energy? We don't know. Really, we don't know. This is one of cosmology's biggest mysteries. Perhaps the biggest. Dark energy makes up 72% of the universe. So 72% of the universe's total energy matter content is dark energy. Dark matter is 23%. Normal matter, stars, planets, you, is only 5%. So most of the universe consists of things we don't understand. And dark energy has negative pressure, meaning it pushes. It expands space. And this pushing force is overcoming gravity. Result? The universe is accelerating its expansion. Physicists accepted this. They awarded the Nobel Prize. In 2011, Perlmutter, Schmidt, Rees, for the discovery of dark energy. And we built a model, the Lambda CDM model. Lambda represents dark energy. CDM represents cold dark matter. Cold dark matter. Lambda CDM is the standard model of modern cosmology. It explains the universe's past and future. And according to this model, the universe's end looks like this: the Big Freeze. The universe will expand forever. Galaxies will move farther and farther apart. Stars will burn out. Black holes will evaporate. The universe will approach absolute zero. Cold, dark, silent, dead. This is the scenario physicists have accepted for 25 years. But now something has changed. In 2024, DESI, the Dark Energy Spectroscopic Instrument, published new data. DESI is in Arizona, at Kitt Peak National Observatory, a giant telescope equipped with 5,000 robotic fiber optics. Its mission? To measure millions of galaxies, to measure their redshift, to reconstruct the universe's expansion history. And what DESI found shocked physicists. Dark energy's strength isn't constant. It's changing over time. And even more shocking, it's weakening. In the Lambda CDM model, dark energy is constant. The W parameter is -1. It's the cosmological constant. It never changes. But DESI data shows that W is greater than -1. It's approaching 0, meaning dark energy's strength is decreasing. If this is true, there are two scenarios. First scenario, dark energy continues to weaken. Eventually, it reaches 0, and expansion stops. Second scenario, dark energy passes 0. It becomes positive, and it becomes attractive. And in the second scenario, what happens? The big crunch. The universe will stop expanding. Then it will start contracting. Galaxies will accelerate toward each other. Space will shrink. Temperature will rise. And eventually the entire universe will collapse into a single point. Time will end. Space will vanish. Everything will merge into a singularity. The big crunch. Exactly the opposite of the Big Bang. And this could happen much sooner than the Big Freeze. According to DESI data, if dark energy continues weakening, the Big Crunch could begin within 100 billion years. 100 billion years. Sounds very long, but on a cosmic scale, very short. In the Big Freeze scenario, the universe would live for trillions of years, perhaps forever. But in the Big Crunch scenario, only 100 billion years. And even more worrying, dark energy's weakening could accelerate. If the W parameter rapidly crosses 0, the Big Crunch could come much sooner. Perhaps within 10 billion years. 10 billion years. The universe's current age is 13.8 billion years, so the universe might live only twice its current age. This is a cosmological crisis, because we have to change all our models. We have to understand what dark energy is. Now there are different theories. First theory, quintessence. Quintessence is a dynamic dark energy theory. Dark energy is a scalar field. It changes over time, and its potential energy is decreasing. This fits DESI data. The W parameter changes over time, initially -1, but over time it approaches 0. And if quintessence is correct, dark energy could eventually disappear. Expansion could stop. Second theory, phantom energy. Phantom energy is much stranger. The W parameter is less than -1, meaning dark energy's strength is increasing over time. And in the phantom energy scenario, the universe's end is much more dramatic. The Big Rip. Dark energy becomes so strong that it tears apart galaxies, tears apart stars, tears apart planets, even tears apart atoms. The universe literally rips apart. Everything fragments down to the quantum scale. But DESI data doesn't support phantom energy. The W parameter appears to be greater than -1, not less. Third theory, modified gravity. Maybe there's no dark energy. Maybe Einstein's general relativity is wrong at cosmic scales. Maybe gravity laws change at very large distances. And this explains the accelerating expansion. This theory is called modified Newtonian dynamics, MOND, or modified gravity. But most physicists don't believe this, because general relativity has succeeded in every test. Gravitational waves, black holes, everything confirms Einstein. Fourth theory, multiverse. Maybe our universe isn't unique. Maybe there are infinitely many universes, and each has a different dark energy value. We live in a universe where dark energy allows for life, because in other universes life isn't possible. This is the anthropic principle. It explains why the universe is this way, because it couldn't be otherwise. But this doesn't satisfy physicists, because it can't be tested. We can't observe other universes. So what's the truth? Honest answer, we don't know. DESI data is new, still being debated. Maybe there are systematic errors, maybe statistical noise. Other observations, the Planck satellite, Hubble Space Telescope, James Webb, haven't definitively confirmed DESI yet. But if DESI is correct, it will revolutionize cosmology. Because if dark energy isn't constant, the Lambda CDM model collapses. A new model is needed, and the universe's future could be completely different. Not the big freeze, the big crunch. Now let's detail the big crunch scenario. Let's say dark energy is really weakening. The W parameter is approaching 0. What happens? First stage, expansion slows. Galaxies are still moving apart, but the speed is decreasing. As dark energy weakens, gravity becomes more effective. Second stage, expansion stops. At some point, the expansion rate becomes 0. The universe reaches its maximum size. It stops, in equilibrium. But this equilibrium is unstable, because gravity is still pulling, and dark energy is no longer pushing. Third stage, collapse begins. Gravity wins. Galaxies start accelerating toward each other. Space shrinks. The big crunch has begun. Fourth stage, galaxies collide. Within billions of years, galaxies start colliding. Giant galaxy mergers. Stars collide. Black holes merge. Cosmic chaos. Fifth stage, temperature rises. As space shrinks, the universe heats up. The cosmic microwave background radiation, the remnant of the Big Bang, heats up. From minus 270 Celsius to 0 to hundreds to thousands. Sixth stage, matter breaks down. The universe becomes so hot that atoms can't survive. Electrons are stripped from nuclei. Then nuclei fragment. Protons and neutrons split into quarks. The universe turns into quark-gluon plasma. Just like in the first seconds of the Big Bang. Seventh stage, singularity. Eventually, the entire universe collapses into a single point. Infinite density, infinite temperature. Space-time curvature becomes infinite. Singularity. Time stops, space vanishes. The laws of physics collapse. And then, we don't know. Maybe a new Big Bang. Maybe a cyclic universe. Expansion, collapse, expansion again, or maybe nothing. This is the big crunch scenario. But will it really happen? Answer, maybe. DESI data is serious, but not definitive. Other observations are needed, especially the Euclid satellite. The European Space Agency's Dark Energy Mission, launched in 2023, and the Nancy Grace Roman Space Telescope, NASA's Next Generation Telescope, will launch in 2027. These observations can confirm DESI or refute it. If dark energy's weakening is confirmed, cosmology will change completely. If not confirmed, the Lambda CDM model will survive. The big freeze scenario will remain valid. But right now, there's uncertainty. And this uncertainty is the essence of science. Because science doesn't give certain answers. Science seeks the best explanation. And as data changes, the explanation changes. 25 years ago, we discovered the universe was accelerating. We discovered dark energy. And we changed our models. Now, we're seeing dark energy weakening. And maybe we'll change our models again. This is scientific progress. But one thing is certain. The universe's end will come someday. Whether big freeze, big crunch, big rip, the universe is finite. And this is a philosophical truth, because we are temporary beings, on a temporary planet, in a temporary galaxy, in a temporary universe. But this doesn't mean meaningless. On the contrary, it means meaningful. Because we are the universe's way of knowing itself. As Carl Sagan said, we are made of star stuff. We are a way for the universe to know itself. And now we understand the universe, its past, its future, its end. We're measuring dark energy, monitoring expansion, modeling the Big Crunch scenario. This is an incredible achievement. A 13.8 billion-year-old universe understanding itself in the last 100 years. And maybe we'll solve the mystery of dark energy. Maybe we'll measure the W parameter exactly. Maybe we'll predict the universe's end with certainty. Or maybe we'll discover something new. Something more mysterious than dark energy. Deeper. Because the universe is always full of surprises. Hubble discovered the universe was expanding. Surprise. Perlmutter, Schmidt, Reese discovered expansion was accelerating. Surprise. DESI discovered dark energy was weakening. Surprise. And in the future there will be more surprises. Because science never ends. Every answer brings new questions. And that's beautiful. Because curiosity is humanity's deepest drive. Why does the universe exist? How did it begin? How will it end? These questions have been asked for thousands of years. By philosophers. By religious leaders. By scientists. And now we're approaching answers. Telescopes. Satellite systems. Supercomputers. Mathematical models. We're solving the universe's secrets. But at the same time, we're realizing how much we don't know. Dark matter. Dark energy. Quantum gravity. String theory. Still unsolved problems. And maybe we'll never fully solve them. Maybe some questions exceed humanity's capacity. Maybe the universe is too complex to fully understand itself. But that shouldn't stop us from trying. Because the search is more important than the destination. And DESI's findings, dark energy's weakening, remind us the universe is dynamic, variable, unpredictable. And our understanding is always temporary. But that's science's power. We can be wrong. And we can admit we're wrong. And we can correct it. If the Lambda CDM model is wrong, we'll change it. If the Big Freeze scenario is wrong, we'll accept the Big Crunch. And we'll predict the universe's end the best way we know. Because that's honesty. Scientific honesty. Being able to say I don't know. Being able to say I might be wrong. And that's bedrock. Where explanations end. Where certainty doesn't exist. What is dark energy? We don't know. What exactly is the W parameter? We don't know. How will the universe end? We don't know, but we measure, we observe, we model, we predict. And maybe someday we'll know. Or maybe we'll discover a new question. And the search will continue, forever. Did the universe's expansion stop? We don't know yet, but we're searching for the answer. And that's enough.